Characterization SRD, page Y380 from AS1204I that will be submitted to Dr. Anziati binti Saroni. Let's begin the video presentation. Assalamualaikum and hello everyone, I'm Izzat, and in this video presentation, we'll be exploring one of the most important techniques used in material analysis, X-ray diffraction or SRD. So what is SRD? SRD is a powerful analytical technique that allows us to examine the external structure of crystalline materials. It helps us to understand important characteristics like the material space composition, degree of crystallinity, crystal structure, grain size, and strain. This technique is widely used in material science, geology, chemistry, and pharmaceutical industry, not just for research but also for quality control. WATA is identifying the unknown compounds of verifying the purity of the product. SRD plays a crucial role. In today's presentation, we will take a closer look at how SRD works, how it's applied to real-world scenarios, and what the future holds for these technologies. Let's begin by looking at how it fits into the broader fields of the scientific instrument and application. Assalamualaikum and hello everyone.
Scientific instrumentation and application concepts. First, crystalline structure determination. X-ray diffraction (XRD) is an important tool for studying both amorphous and semi-crystalline polymers. It can be used to analyze many features of the microstructure of the material, including lattice perimeters, presence of imperfections, crystallographic orientation, texture, and degree of crystallinity. Second, forensic science. SRD is used mainly in contact trace analysis. Examples of contact traces are paint flakes, hair, glass fragments, stains of any description, and loose powdered materials. Identification and comparison of trace quantities of material can help in the conviction or exoneration of a person suspected of involvement in a crime. Lastly, glass industry. While glass is X-ray amorphous and does not itself give X-ray diffraction patterns, there are still manifold uses of XRD in the glass industry. They include identification of crystalline particles that cause tiny faults in bulk glass and measurements of crystalline coatings for texture, crystallite size, and crystallinity.
Assalamualaikum warahmatullahi wabarakatuh. My name is Wan Nur Khalid bin Wan Kamrudin, and I will explain about detailed exploration of material characterization (SRD). First, glazing incident SRD, a technique where the incident angle of the X-ray beam is very small, so the X-ray only penetrates a short distance into the material. This allows you to analyze the top surface and thin layer without interference from the bulk material underneath. Second, in situ SRD, a technique involves performing SRD measurement while a material is in the process of being charged or treated, rather than after. The goal is to observe dynamic processes such as crystallization, crystallization, thermal expansion, and reaction. That's all for me.
Assalamualaikum. My name is Muhammad Badar Rizal, and today I would like to talk about the examples of real-world implementation of XRD. The first one is pharmaceutical industries. Their application are to identifying polymorphs that affect drug solubility and stability. It is done to ensure the quality of the drugs produced by the company, and also ensuring consistency between drug batches. For example, ritonavir's polymorphic shift caused a major recall due to reduced bioavailability. Second, battery and energy storage. Their application are monitoring phase transitions in materials like lithium-ion battery during battery recycling, and also analyzing degradation and structural stability of the battery. For example, research labs and battery manufacturers use in-site XRD to study material behavior. Okay, on to the next one. Now, the third examples of real-world implementation is metallurgy and steel industry. Their application are for measuring residual stress in welds to prevent accident from occurring, and also quantifying retained austenite in steels. For examples, automotive and aerospace companies use XRD for quality control and failure prevention. And the last one, semiconductor and electronics. Their application are characterizing thin films for microelectronics and also ensuring uniformity in epitaxial layers. For examples, foundries and chip manufacturers rely on XRD to monitor material properties at the nanoscale. That's all. Now, I will talk about the benefits and also the challenges when using material characterization XRD. The first benefit is that it is non-destructive testing, which means it does not damage or alter the samples when used. Second, phase identification, which means it accurately identifies crystalline phases and compounds, and also it is critical to understanding material compositions. Now for the challenges. The first challenge is peak overlap and complexity, which means overlapping diffraction peaks can make phase identification difficult, especially in complex or combined mixtures. Now the second, cost and accessibility. High precision XRD instruments can be expensive and often require skilled operator for interpretation, which means you can usually found this as which means you can usually found this instrument in private hospitals.
Future developments and innovation. First, increase speed and efficiency, faster data processing, improvements in data acquisition and processing speeds will allow for quicker analysis and higher throughput. High throughput system can automate and robotic system will be developed to reduce manual intervention and increase the number of samples analyzed. Second, enhance precision and resolution. Higher resolution output can development in detector technology will lead to more detailed and accurate SRD patterns, allowing for better characterization of PF materials. And improve sensitivity, new techniques and instruments will enable the detection of smaller quantities of materials and finer details in material structures. Next, advancement in specific application. Portable SRD, on-site analysis for mining, construction and environmental monitoring will become more common with the development of smaller, more robust portable systems. And non-ambient studies, SRD system capable of analyzing materials under extreme conditions like temperature, pressure, humidity will expand the scope of applications. And lastly, new SRD techniques. Hybrid SRD or HSRD, these techniques aims to analyze materials without extensive sample preparation, potentially revolutionizing analysis in fields like geology. SXCT and PDFCT, this technique extends SRD to study materials at different length scales, providing more detailed structural information.
In conclusion, SRD diffraction or XRD is a valuable and non-destructive technique used to analyze the internal structure of crystalline materials. It helps to determine the important characteristics such as the phase composition, crystallinity, grain size, and internal strain. This makes SRD essential in understanding material properties and improving product performance. It is widely applied in fields like material science, geology, chemistry, and pharmaceuticals, supporting both research and quality control efforts, although the technique has certain limitations, such as being unsuitable for the amorphous materials and requiring expert analysis. Its benefit make it independent tool, with the continuous advancement in technology, including AI integration and portable systems. SRD is expected to remain at the forefront of materials characterization and innovation.